Ahora sí.
Okay, so our next speaker today is Arie Worstman, also former student from here, from Dean, who is doing his PhD at the École Normale Supérieure in France. And Arie is going to speak about feature learning with a structured covariance. Please, Arie. Thank you.
Thank you very much, Fagin. Well, I must begin by thanking the organizers for inviting me. It's always a pleasure to talk in Chile. I hope this occasion can happen again in the future, hopefully in person. Well, for now, I have to be happy with presenting my results online. So before I begin, also, I want to specify that part of this work, we began doing this like last June, I think, last May, during my internship for the master's here in Paris. And we are currently like finishing this right now that I'm beginning my PhD with Bruno. Okay, so, well, this is joint work with Bruno Loureiro. He's my PhD supervisor at ENS. Well, also another, like, it's a warning, I should say, not because my results will not be rigorous, but rather because the spirit of the results, it's quite specific. There's a lot of assumptions. So why do we have a lot of assumptions? It's mostly because we're working on this through the site where there's a lot of physicists working with us. And well, physicists, they like doing assumptions. You can think like the Ising model, for example. Obviously, the Ising model doesn't model paramagnetism or magnetism at all. It's way simpler, but one can understand phase transitions through the Ising model. So what we will try to do today is to study neural networks, but in a very specific setting, so we can understand what's actually happening. And so, well, I think that's all I wanted to say at the beginning. Okay, so neural networks are good. We all know that. That's like the baseline of our talk. There's a lot of applications. Most of us use them every day for translation, recommendation systems, everything, right? And if you ask anyone, you could tell ChatGPT, but I will say Google in general. Like if I search in Google, why are neural networks a good model for learning from data? Most of the answers that will come in that search is that they adapt and they learn futures. However, this is very bad specified. Like there's not a real answer, mathematical answer of what does it mean to adapt to the data and what does it mean to learn futures. So first question for us is, what does it mean? Okay, how do we make sense of this? And second, why should learning futures, whatever this is, should be better? There's not a particular reason for that, but we will try to explain during this talk. So the title of our talk is Learning Futures with a Structured Covariance. So a structured covariance means that our data will not be isotropic. For those of you that don't know what isotropic means, I will tell it in a few slides. But what I want to say is that we will check neural networks between two different assumptions. In one of them, we will work in initialization, as I say here. And at the initialization, we will study neural networks as if they were kernels or the so-called random futures, okay? And then we will do only one gradient step, but a very big giant step, as I will tell you in the following. And we will study what happens when we do this step. Is it better or not, okay? Well, there's been a lot of study already about what happens when the data is isotropic. However, doing it in the anisotropic setting has its own difficulties, okay? But don't worry if you didn't understand this slide, because I know there's a lot of you that don't know anything about machine learning. So I will try to start and begin from the very basics, okay? So we have the classic supervised learning setting. We are giving a sample of n data points. So that's the first thing you have to get in your mind. We will have n data points. And we have a probability density, which in this case we will call rho. And our dimension here will be d, okay? We will try to work today in the setting where the dimension is very big. So we will have to use a lot of tools from high dimensional probability, okay? Well, what is the basic goal of supervised learning is to learn a function parameterized by theta, which in this case will live in Rm, so that given a new sample, we can predict it. We can predict it correctly, in some sense. Okay, so mathematically, what does it mean is that whatever is the sense that I define, I have to express it into a loss function, which it's actually defined in our setting in R times R, sorry for that. I will rewrite it correctly so everyone knows. So this takes pairs and it compares it. It compares this pair. And with that, we can compute our population risk. Okay? So our optimization problem becomes the following. We have to minimize an expectation. However, as it's always the case in statistics, we don't have access to this rho. Of course, in my case, we will have it because it will be an artificial case. But in general, in life, we don't have access to it. So that's the first problem, right? We don't have access to rho. So what do we do instead? Well, someone like 100 years ago said like, okay, since we don't have rho, the best proxy we can get from it is empirical risk, which is basically the Monte Carlo approximation of this in our data, right? But there's also a second problem. And the second problem comes from the fact that usually this is a non-convex problem, okay? And why is this a problem? Because optimization is very well studied in a convex setting. Okay, so somehow, however, neural networks and machine learning models overcome this difficulty. So we have to start understanding why. So, well, of course, the ideal setting would be like if we were a first-year engineering student at Universidad de Chile or Universidad Católica or in Chile in general, we would have an optimization course, and they will give us a function like this. We will have to compute a gradient. We make the gradient equal to 0, and we find the maximum or the minimum, right? Well, in the real life, that's not what happens, right? In real life, what we have to do is to use some sort of algorithm to find this minimum. The most common algorithm is gradient descent. So basically, you take your n data points, you take the empirical risk, and you compute this gradient right here, okay? And you put here a step size, okay? Someone in the chat before asked, how do you choose this step size? There's a lot of heuristics for this, but in general, it has to be not small, not too small, but not too big either, okay? Now, computing this gradient is not necessarily easy because n can be very large, especially today. We have a lot of data, right? So how do we overcome this difficulty of computing this gradient? Is by doing what is called stochastic gradient descent. So in stochastic gradient descent, we will take a subset of these samples, which could be 1, could be 10, whatever you want. This is called a mini batch, and we will approximate this, okay? So intuitively, if you want also, this is optimizing our real population risk. Why? Because this in expectation, all of this, if we took expectation of this would be actually the expected gradient for the population risk, okay? So this is the benefit of stochastic gradient descent. Today, we will study a combination between both. You will see why I say this in a moment, but let's say we're talking about SGD. Okay, so in any supervised learning problem in learning theory, as I'm going to talk to, like the one I'm going to talk to you about today, we have to ask ourselves 3 questions, which are very related. There's no other particular order, but we need to ask them. First question, the training algorithm. How do we find the correct function we want? How do we find a good function for our loss? The second question is sample complexity. How much data will I need? If I choose a specific model or a specific algorithm, and it turns out that I need 1 million data points and I don't have them, this is a problem, right? And number 3 is the architecture. What kind of model, what kind of family is the family of functions that is in this, to which my parametric model will be part of? Okay, so today, this question is like our main question. We will try to solve this question. But for the other 2, we will have a fixed setting, okay? So for the training algorithm, we will choose stochastic gradient descent. We will ask ourselves about the sample complexity when the architecture are either kernels or shallow neural networks. So I know a lot of you don't know anything about kernels or shallow neural networks. So I will start from the very basics of this, and I will construct neural networks starting from kernels, okay? So that way you will be able to understand what I'm going to talk to you after. Okay, so kernels. The idea of a kernel is to build functions in this family that are linear in their parameters, meaning this, okay? Now a detail. I'm only saying here that H, this H here, is a Hilbert space. It could have any dimension. I'm not specifying anything about H. I'm only saying it's a Hilbert space. It could be an infinite dimensional space. It usually is, in fact. The problem is, this is usually an infinite dimensional problem. So how do I tell my computer to run an algorithm to solve something that is infinite dimensional? It sounds crazy, right? Well, it turns out it isn't that crazy. Why? When we see our function, our loss function right here, we're looking for something like this, right? But if we actually expanded this loss right here, well, also before saying that, I must tell you that this is kind of a regularization. So what we want is to select a theta that somehow is not interpolating data, but has good properties. Like we don't have to overfit. We don't want to overfit the data, okay, into the data. So now what I was going to say before, this loss function right here only access this pair through dot products. Okay, then maybe the better way to define this is through this function right here. And this is what we will call a kernel, okay? Then the optimization problem, defining this, can be transformed in this problem right here, which is for alpha in Rn. So we passed from optimization in an infinite dimensional space to optimization in Rn, okay? This is called kernel-rich regression, okay? And this is very famous. It has existed for at least 60 years, okay? Maybe 60 years ago, they weren't using it as today in statistics, but kernels and the idea of kernel-rich regression has existed for a long time, okay? So we have our finite dimensional problem, and we want to solve it, okay? Once we solve it, there's a very nice theorem called the representer theorem, and this theorem tells us that the prediction function that we will get will have this form. Okay, so we get our alpha here, and this alpha then we put it in our function. You see, this is what we wrote as, could be written in the notation of before as this. Okay, so there's a lot of different kernels. There's a whole slew of different kernels. But for example, some particular kernels would be the linear kernel, which could be just doing linear regression, as we all know, and we all see in statistics 101. Or it could be the polynomial kernel, for example, which is a lot more complicated, and actually could fit a lot more functions. Okay. Now, today I will talk about very specific kernels. But before talking about these very specific kernels, I want to introduce you to random filters. A lot of kernels in the literature, and when I mean a lot, I mean most of them, can be represented as an integral over a measure, like this. Okay, so this is a product in L2. Okay, but we don't know how to deal with this. Okay, we don't know how to deal with this because it's an integral. The best way to compute an integral for a probabilist, for you at the public today, you're a probabilist. So I tell you, I need to approximate an integral. What should I do? You would tell me, well, you could use Monte Carlo because this is a measure. Okay, so I take data points, different data points. I take m data points, and I approximate this integral as an average, and I get this. This idea was introduced in 2008 by Ali Rahimi and Benjamin Recht. And at the moment, it was done because they wanted to make the computational problem of optimizing with kernels easier. What do I mean with that? By that, sorry, but because of the change of slide, is that this should be important only if it's computationally efficient. 20 years later today, we see that this is actually important for studying the generalization of neural networks, which we'll see in a moment. Okay, so as a summary for random filters, we change this infinite dimensional problem by the Monte Carlo approximation right here. And the filter representation has this explicit form. Okay, so we solve this explicit problem, which is a lot simpler. And note this, it's in practice, computationally, it's easier only if the number of filters is less than the data. Okay, so this is called the underparameterized regime. If m is less than n, this is computationally efficient. okay, because of the form that the function gets when one optimizes a kernel. Today, this is not the case anymore. That's why I say a priori. Okay, now let's see a particular case of random filters. If I give you a function sigma, which we will call the activation function, and I consider this kernel right here, where this measure tau right here is the uniform measure on the sphere. Then, if I sample p data points from this measure, I will get different parameters, w, and the filter maps will be these guys right here. Now, this sounds familiar for some of you, probably. This is what we will define as a shallow neural network, okay? So as you can see, we can construct neural networks as random filters. What I mean by this is that at initialization, when I initialize my parameters, I'm actually using random filters. And if I optimize on the second layer, I would be doing random filters, okay? That's why random filters will be important today. Okay, now a word about neural networks. I could have started my talk by talking about neural networks specifically, but nothing of what I will say in the future right now will be meaningful if you don't know that they are random filters at initialization. Okay, so what are the common words in neural networks? Well, first of all, these weights right here, we will call them the weights of the neural network. This right here will be the output weights. Sigma will be called an activation function. And typically, sigma will be this function right here, to be honest. This sometimes, but this one is the most important. It's called the ReLU. Okay. So now let's talk about our setting today. So we have a neural network with P neurons. There should be a P right here. We have a neural network with P networks, and we want to study its properties in general, about before and after training. So why do we want to study this? Why do I mention future learning? Okay, so I think I have to stop here for a moment and talk to you about this, which is called the lazy regime. Okay, so in 2018 and 2019, two different groups of researchers started studying neural networks and got a lot of results. There's extensive literature here in this area of what is called the lazy regime. So basically, what does the lazy regime say is that neural networks are well approximated by kernels at initialization. And that actually, under some parameterizations, neural networks never leave this setting, and actually they are well approximated as a kernel at initialization. So essentially, this literature is telling us that it's not important if you train these W's or not. If you train this, you're a kernel and we can study you. Okay, and there's a lot of generalization properties of this. The problem is, in practice, we're not seeing this yet. In practice, we're still seeing neural networks that outperform kernels by far. So why is that happening? Well, what's happening here could be described somehow if we study things from a non-asymptotic way. What I mean by that is that most of these models right here, they take the limit when P is very, very, very large. So today we will try to fix P to be large, but not as large as kernel methods. And we will study what happens when we train this model, okay? So we will do stochastic gradient descent in this W, and we will compare what happens after the gradient step and before. So basically we have two kernels, we have two random filters of the very different distributions. What we will compare is if the second one, the trained one, is better than the first one. Okay, so in general, this is what we will call the teacher model, okay? So I must tell you that I'm using this terminology, the teacher and the student. This terminology is actually borrowed from physics, from statistical physics, okay? It began like in the 70s for the first models of neural networks in the works of Derrida, okay? So the teacher, in our case, will be a specific function. And this is what I meant in the beginning, when I told you that I will be doing a lot of assumptions, okay? I will be actually telling you which function we are learning. What's the type of function we're learning? Why? Well, because we want to really know what's happening here. So we will assume the input data, it's Gaussian. Why Gaussian? Because we know how to compute things with Gaussians. Okay, that's the only reason why we're choosing a Gaussian distribution. Okay, and we will choose targets, which will be generated by the so-called multi-index model. What does it mean? It means this is a function of a low-dimensional projection of the data. So this is a low-dimensional projection. Okay, so philosophically, one would expect that this is the type of model one learns in the real life. Okay, so in real life, our functions are not extremely complex. They only depend on a finite number of directions, and we need to find those directions. Okay, so that's the first good reason why we should study this type of models where the target function is given by a low-dimensional projection. Okay, number two is that in 2017, Francis Bach here in Paris, he proved that when one works with kernel methods are not able to adapt to this type of structure. Okay, so if neural networks were able to adapt to this type of structure called the multi-index model, then they would be then we should use neural networks and not kernel methods for this type of models, right? Also, think about it philosophically. If we want to learn this model somehow, we need to learn this. And learning this is what we will call further learning. Okay, so more on this in a moment. So we have the teacher here, and we have the student, okay, which is a two-layer neural network. So our questions will be the following. First of all, how much data, what sample complexity is number of data. So how much data do we need in order to make these weights align with these weights? Okay, we need to learn these weights in order to learn this function because it's low dimension. Okay, so we want this to align with this. This is what's called weak learning. And number two, this is one question. Okay, separate question. Does one step of SGD make the resulting kernel better or not? Well, our training algorithm will be the following. So we take data, we do one gradient step with step size eta. Don't confuse eta with n, okay? This is a problem, and when you write it actually in the board, you have to change names. But here, I think it's clear that this is eta, this is n, okay? After one step of SGD, we will train the second layer by doing ridge regression. This way, we are doing what in Chile we call comparing apples with apples and pears with pears, okay? So we have two kernels, one after the stochastic gradient descent step and one before. And important observation, if we didn't do this step, we would have random futures, okay? So now let's talk about the results that already exist in what I'm going to do. So most of the results work where we use Gaussians that are isotropic. Isotropic, for those of you that don't know, means exactly this. The covariance, it's equal to the identity, okay? So essentially in higher dimensions, what happens is you're on the sphere, okay? You're in the sphere in RD. And this has been extensively studied the last years, okay? So let's review what's been going on in this area. First of all, for random futures at initialization, neural networks at initialization. For isotropic data, you need a polynomial d to the kappa to learn an approximation of degree kappa of the target function. Okay, mathematically, this means this. Okay, which means you need n proportional to d to the kappa to learn the best kappa polynomial that approximates your function. If this function was a polynomial of degree kappa, then you could learn it completely only by using n and p of order d to the kappa. Okay, so you would need a lot of data and a lot of neurons. Now, one usually is not in this setting. We usually don't have that many neurons because we are using computers, and computers have natural limitations. And we don't have that number of data because, well, there's not that much data in general. Sometimes there is, but in general, there isn't. Okay, so let's work in the particular regime where n and p are proportional to the dimension. This is actually acceptable. Like if you look to a very large image, even if it's extremely high resolution, and the kind of neural networks that we're using for this is actually the case. We're like more in the proportion. Okay. Also, this regime fits very well into random matrix theory, which is a very important tool in the future. Okay. So if we're in this regime, we can learn a linear approximation of the function. Okay. What's the intuition behind this? Well, this uses tools from probability theory, but the intuition here is not from a probabilist. It's from a physicist at all. It's not from like from any point of view. Okay, so since this is Gaussian, one can use an Hermite decomposition of this into polynomials, orthogonal polynomials, and this right here will exhibit a decay. Okay, because we're in high dimensions and things concentrate. This is the intuition. So we will be able to approximate this model as a linear model. This is what Javier called before universality. Okay, and it's essentially a central limit theorem. Okay, but not the usual central limit theorem we are used to. It's a different type of central limit theorem. Okay, I can talk about more about that in the future. But for the moment, this type of universality results, they began in 2022 with the work of Loureiro et al. And there's a lot more works, but I think the most important one is Hu and Luz in 2023, which actually were the first one to give a rigorous proof to this argument. And there's also Montanari in 2023. Okay, so all of them, they found out different ways to prove essentially this. Okay, in the proportional regime, when n and p are proportional to the dimension, then this activation function can be very well approximated by a linear function. Okay, so the message here is random filters can learn everything you want, but they need a lot of data and a lot of neurons. If we find out that after one gradient step, we need less data or less neurons, then neural networks are a better model for multi-index models. Okay. Okay. Now let's do one step of SGD. That was a picture for initialization. Now we do one step of SGD. So it's the first part of our algorithm. And what we find is that in the proportional regime, in 2022, a lot of authors proved that if this step eta is small, then you will be better than random filters, but you will not be able to learn more than a linear approximation of your function. So you're better, but you're not extremely better. However, after one gradient step, if your step size is big enough, it's order of d, then yes, then you're able to learn a lot more than a linear function. To be more precise, if eta is big enough, then after one step, our weights, W1 right here, have a strong correlation with these weights. Here, PV star is the projection on the span of the teacher weights. Okay, so this result is telling us after one step, you can build correlations, you can have future learning. Okay, so in general, actually, we can extend this beyond the proportional regime by using what is called the leap coefficient, which will be the first non-zero coefficient, Hermite coefficient of F star. Okay, and if you think about it, this first non-zero Hermite coefficient, it's measuring how complex the function you're learning is. If the leap index is, I don't know, 6, it means your function, it's a very high degree polynomial for Gaussian data. So it's very difficult to learn it. You will need a lot of data. But if you have L equals 1, you have a linear part, and you can learn that. Even more, you can actually characterize how many directions you will learn after one gradient step. So the picture, this is from a paper by Dandy et al. This is a very big group, sorry. And okay, so the picture is the following. If you have less than O of D data, you will not be able to learn the directions. You can't build correlations. If L equals 1, so if the first Hermite coefficient is non-zero, you can only learn a linear subspace. So what that means is you will build correlation, but you will only learn one direction. Okay, you can actually find that direction explicitly all the time. Okay, but I will not enter into that kind of details. If L is greater than 2, then actually our neural network in this region can learn a lot more than one direction. Okay. So once again, in the proportional regime, which is the usual regime, the best we can learn is a nonlinear function of one direction. It's this case right here. Okay, but we can learn a nonlinear function. This is already why neural networks separate from the kernel regime at initialization. Now, our generalization of these results works with anisotropic data. What that means is that we change the identity. So we have, before we have this, now we say we don't want to work with this, we work with this. Okay, for some covariance. Okay, why should we do this? This is adding a lot more structure to the problem. Okay, why? Because before the structure of the problem was completely centered in the target function, which was a multi-index value. Now, if we give a covariance, then the problem has a new layer of structure, which is in data. Okay. Also, the second reason and the most natural one is most data in real life is not isotropic. Okay. So maybe if our results show that some kind of covariances are better, then that would mean that neural networks are even better than we thought before for isotropic data. So there has been a lot of work lately in this area, but the two works that I would highlight would be these ones by the group of Ba. These are the same group, actually. We studied what happens in the simplest anisotropic setting. The simplest anisotropic setting would be to say that sigma is the identity plus a perturbation. So let's say mu and some vectors v and vt. Okay, so this is a TensorFlow. Okay, so you take the identity, you perturb it in one direction, and you have to see if things work better or not. Okay, in our case, what we will do is to put a power law structure in this covariance. What this will mean is that we will still have a diagonal covariance, but at the if entry of our diagonal covariance, we will have a constant which will depend on d times e to the minus alpha. So there's a decay. We start with a very big eigenvalue, but we start decaying until the last one, okay? So we can do this for alpha greater or equal to 0. Our results, actually, the isotropic results will be a corollary of what we were doing, because if you take alpha equal to 0, then you will have exactly the identity, okay? And this constant right here, we built it so the trace is always equal to d. Now, a lot of you will tell me that putting this normalization in the covariance is very artificial, but it isn't. In statistical mechanics, in physics, and probability, we usually need correlations to the order of 1. If you don't put this kind of normalization here, then this could be going to 0. So we are not observing the phenomena as we wanted. We are the scale we need is this scale, where this is order of 1. Okay. So by applying the same techniques as before, we get similar results. We get that for initialization for random feeders, when n and p are proportional to d to the kappa, one can learn the degree kappa of this function. And for some k or alpha, also we could learn a higher part, okay, a higher degree. Now, this sounds a little bit confusing, but I will show you a picture in a moment, and I think it will be a lot clearer. Also, this looks like a very pessimistic result. This looks like, well, if it's not easier for kernels, then why should it be easier for neural networks? However, note that because of this decay, variance in our data is very concentrated in the first components of our covariance, not in the last ones. So what's the most usual tool data scientists use? It's not neural networks even. It's not a classification or a regression model. It's PCA. If you did PCA in your data, your model could be better. It's usually better if you do PCA before training your model. Why is this? Because essentially you're deleting all the data that has low variance. So we don't care about this because the final result will not depend on these directions, which are basically constant in the infinite dimensional limit. Okay, so actually, when alpha is greater than 1, and we already proved it, when alpha is greater than 1 and we are in the proportional regime, and f is a polynomial, you can learn it completely. And as d goes to 0, the population risk will actually go to 0. Okay, so the result is not as pessimistic as it seems, because there's a lot of data that we need a lot of signal to see data that have very, very small covariance. You need a lot of data to do that because the covariance is very small. So to zoom into that scale, you really need a lot of data to take conclusions out of it. Okay, but the question is it really important for generalization? No, it isn't, because the covariance is small. So as a summary, for the isotropic case, essentially when data was O of 1 here, we weren't learning anything until data was O of D. In this case, we ended learning the degree 1 and we began learning a degree 2 approximation of our target function. When we go all the way to D squared, then we finally learn a degree 2 approximation. So as you can see, things are very well separated here. Now, what I was telling you before is that in this case, things are a little bit messier. Why? We begin learning a degree 1 approximation, then suddenly, depending on the value of alpha, you will begin learning a degree 2 approximation until you have O of the data. Then you will end learning the degree 1 approximation, but you're still here. And you will not end this until you have D squared. And of course, maybe right here, you will begin learning the 3rd degree approximation of the data. Okay, so it's a lot messier. And actually, when alpha is greater than 1, with constant data, you begin learning all the degrees. Any degree you want, you learn it with constant data. But you will only learn the best first degree polynomial with D to the alpha. Remember, alpha is greater than 1. So alpha equals to 2, for example, would mean that to learn the complete degree 1, one would need to have D squared data. This is crazy, right? And this is because, as I told you before, you need a lot of data to really zoom into that direction that has such a small covariance. The question is it worth it? No, not at all, because in the end, this will essentially be 0 in the risk population, in the population risk, sorry. And so, now, what happens after one gradient step? Since the random filters case, the population risk goes to 0, we will only focus on the case where alpha is between 0 and 1. Okay, so our quantities, which is not the case in the isotropic setting, will not scale with D, but rather with an effective dimension, which is this one right here. Now, we are not the first ones to introduce this effective dimension. There's a lot of literature on this, and in a lot of physical problems, this appears naturally. Okay, so in general, this effective dimension is O of D for alpha less than 1/2, but if alpha, the decay, is bigger, then the effective dimension is a lot less than the dimension. And actually, just a word about it. Well, I know I said I was only talking about this, but if you took alpha greater than 1, then the effective dimension would actually be a constant. So the effective dimension is measuring the dimension of our data for our algorithm. For a neural network, for example, the dimension will not be D, but rather a reduced version of it, a little less than D. Okay, so recall in our setting, we have data with a covariance, which has a power law, and we have our teacher model, which is a multi-index model. So we proved this theorem, which says if n is proportional to the effective dimension, p is proportional to the effective dimension, and eta, the step size, is proportional to the effective dimension, then you can build correlation. Then you have quick learning. So it's very interesting because we added more structure into the input data, and things actually started becoming easier. Now, about this picture that I showed you before, does this change? Can we learn more than one direction? Well, actually, this picture stays the same. The only difference is that instead of D, here we will have the effective dimension. And here we will have the effective dimension squared, and so on and so on. Okay, so now everything I'm telling you, it's worthless if I can't prove it experimentally. That's the computer science mind. So what the computer scientists tells us is any kind of theory you do, you have to do experiments on it. Okay, so this is what we're going to do now. Here we're learning the Hermite-1 polynomial. I'm sorry, this is PO1. So Hermite-1 has leap index 1 because it's the definition of a leap index 1 function. Okay, so here we have a constant number of samples, and we take alpha equals to 0. So this column right here is the isotropic data. Okay, so for isotropic data, when we take, this is O of D in this case. So when we take data proportional to the dimension, we can build correlations. Okay, but look at the other ones. In this column, this is O of DF, always. Okay, so the effective dimension when alpha equals to 0 is actually the dimension. Okay, so in this case, for example, with data proportional to the effective dimension, we already started learning. Okay, you can do the same for L equals 2. And well, this is a lot more illuminating because as you can see, when L equals 1, as I told you before, you will only learn one direction, which is this setting. When L is greater than 2, one can actually find a lot of directions in your data. Okay, so what are our next steps? What are we doing right now? Well, first of all, does it work for more general covariances? I'm pretty sure it does. I think I need to check some arguments, but yes, I think we could put any kind of covariance you want there, and this quantity, the effective dimension, will appear all over again. Second type of question. Generalization bounds after one gradient step. What will be the population error after doing one gradient step? Well, this is a lot harder. Why? Because the kind of generalization results that one usually has for neural networks are not very well defined in our setting because most of the results use isotropic data. Okay. Some people extend what is called Gaussian equivalence, the universality result I showed you before, and they use the what they call the conditional universality or conditional Gaussian equivalence. But in our case, Gaussian equivalence may not even be true for some values of alpha. So these kind of tools, we can't use them. So, well, if you want, in the questions, I can tell you more about what we think is the correct approach, but I insist that this is not yet done. Also, what happens after many steps? Why do we only choose one? We could have chosen 20 steps, 19 steps, whatever you want. We only chose one. What happens if we do more steps? So, now ending my talk, some conclusions that I want to tell you. Well, first of all, first take-home message is neural networks are actually better than random filters at initialization. Okay, and only after one gradient step. So imagine what happens after 1,000, which is the usual case, especially for a multi-index model, both in the isotropic case and in the anisotropic case. Number two, the amount of data we need to establish correlation with the teacher weights does not scale with D, but rather with an affective dimension. And well, I think that's all I want to tell you today. So if you have any questions, I'd be happy to answer them. Also, well, thank you very much again for inviting me. And if there's anything that was not clear, you can tell me. I have no problem in explaining anything. So thank you very much.
Thank you very much, Arie. Are there any questions? I have a couple of questions. Yeah, what is your intuition about what happens when you said you are taking finite p, but if you let p go to infinity, your normalization was similar to neurotangent kernel. So what would you expect how would you expect to see or extrapolate what happens with one step when you go in that regime where you really are like in the continuous?
Okay, that's a very good question, and the answer depends actually on the scale at which you go to infinity. So the NTK regime, for example, it requires a polynomial scaling with the dimension. Okay, so if you just take p to infinity linearly with the dimension, that's not a problem. You won't enter the so-called lazy regime where you don't want to be. Okay, so I think that kind of answers your question. You could take p to infinity and don't enter the lazy regime. But know that I think a very nice thing about this line of research is that results are non-asymptotic, meaning that you don't actually need to take p to infinity at any point. You just have to state your results in terms of high probability events, which are concentration results, essentially.
Yeah, right. Yeah, so you would be obtaining, I mean, yeah, that was my question. You are not in the, you are doing better than of course, the lazy training regime, but yeah, already from the finite step, and then it's the future line of research that you said. What happens when more steps are done? Okay, and my other question is, I think there is some similarity, but I'm not pretty sure with the conditions in works like, there is this idea of benign overfitting, which is
Yes. Okay, so actually that's a very good question, because the term of the effective dimension, we took it from there. For example, that's the first work we saw it. So yes, in general, we could use this type of results to state some kind of benign overfitting results for neural networks, but I think we're still very far away from that. But yes.
Okay, but it's related. I mean, it's
yes, it's very related. Very related.
Okay. Okay, thank you very much. More questions? Javier?
I had a question, but it's just if you could maybe explain a bit more again the like your numerical experiments. Like you said, oh, we can see where
Sure.
the effective dimension, but how are you seeing that on the diagrams?
Okay, so yes, I think I could have explained that better actually. So thank you very much, Javier. So in this column, we have all of the effective dimension samples. This is all the way here. And in this column, in this row, and in this row, we will have the effective dimension squared. Okay, so essentially what this is measuring is the similarity between student weights and teacher weights. And you can measure that similarity by the cosine similarity. Okay, and the best way to plot this is by this. So if you are in the border of the circle, you're very correlated. If you're in this small ball right here, then your correlation is not big enough, and you're essentially orthogonal in high dimension. Okay, so what we see here is that our limit index was 2. So the first non-zero Hermite polynomial of the target function is Hermite 2. Okay, so what does that mean is that, well, with constant data here in this setting, for example, this is isotropic data, you don't have any correlation with the teacher weights. Then you get linear data. You don't get a lot of correlation. These are basically undistinguishable. You get all of the squared data, and you can build correlation. That's the idea. Now this column is the same. Now you change alpha from 0 to 0.5. So basically now you have a decay. So once again, constant dimension, well, things are almost orthogonal. You start giving the effective dimension, data proportional to the effective dimension. You build some correlation, but not really. Once you have the effective dimension squared, you can start building correlation here. Okay, and this is very cool because you can actually go all the way to any alpha you want. And if you look here, for example, you didn't even train the model, and you already have correlation. This is because actually the teacher weights and the student weights are not really living in D. They're in a very low dimensional subspace. So that's why the orthogonality is not happening anymore.
Thank you very much.
Don't worry. Thank you very much.
Further questions? Otherwise, I was just, you mentioned this sort of universality or central limit theorem or something. I didn't get, like, I'm curious what it is.
Yes. Okay, so actually that's a very, I wouldn't say obscure line of work, but okay, so the idea is the following. Let me go back to what I wrote before. Did I already? Sorry. Here it is. Okay, so what happens is the following. So the universality result, the kind of universality result is what Javier said before. So essentially, what you're proving is that asymptotically on the dimension, you could replace your filters by Gaussian filters with some specific mean and some specific covariance. So this in machine learning, it's called universality, okay? And what this is telling you is that the generalization error of random filters, when D is very, very large, it's almost the same as a Gaussian version of your random filters. Now, why is this kind of universality cool in this area? Because we all know how to work with Gaussians, but anything else, it's very difficult. I mean, just to give you an idea of how hard it is to work with things that are not Gaussian, to go from one step to two steps in this setting, it's very difficult because after one step you're not Gaussian anymore. Okay, so this type of universality results, what tells us is that we can actually work with Gaussians in high dimensions under some assumptions. There's a lot of work in this area, actually, like until I think last week there was a new paper on this. But there's a lot of random matrix theory in this area also. They use like the spectrum of the resulting random filters matrix.
Okay, thanks. Okay, I think there are more questions. So thank you very much, Arie, again. Well,
no, thank you very much for the invitation once again.
Stay online for a while if you want to discuss or whatever. But the talk is over, so thank you again.
Thank you.